Okay, and my slides are visible to you, I hope so.
Yes, they are visible.
Okay, okay. So then let me start from the discussion where I have stopped. So as I told earlier that in this figure I have given a system which is bounded by two walls, and maybe there is a flow. If you think about the real life application, that is this is nothing but some flow inside a channel or inside through a pipe. Any kind of flow through a pipe can be design it as flow or some material inside two boundaries. Okay, so now my aim is to model so this uh, flow or this material through a pipe mathematically, and to understand what is the mathematics behind this simple flow and daily life usable flow, where you can see that there is a wall or a pipe. Inside the pipe there is a flow. In such kind of application, how to model mathematically using differential equation, and how to solve that complicated differential equation using linear algebra and the theory of eigenvalue eigenfunction. Okay, so first thing is to model this kind of flow. This is very common flow in our real life in nature, and mathematically we can model this flow using certain differential equation, and maybe few of you heard about Navier-Stokes equation. So Navier-Stokes equation is nothing but a certain type of partial differential equation which is nonlinear. Many nonlinear terms are present here, which is nonlinear, and they are coupled. Okay, coupled means there are certain variables. So in this case, in this Navier-Stokes equation, variables are like u, v are the variables, and this u, v denotes the velocity of the system. U denotes in x directional velocity, v denotes the y directional velocity, and these velocities are dependent on time and space, and therefore derivative with respect to time as well as derivative with respect to space coordinates like x and y are present in this equation. So Navier-Stokes equation, a coupled nonlinear partial differential equation where there are certain unknowns and certain independent variables. Okay, so unknowns are dependent variables of time and space. Okay, so this Navier-Stokes equation, these three equations we need to represent or to model the complete system which is bounded by two walls and there is something flowing inside the wall. Okay, so this equation has certain meaning actually that I am not going to discuss in this lecture. So these are much more advanced thing, but you just think about that the properties of the material or whatever you are taking between the walls, properties of that material or that substrate can be modeled using these three differential equation, where first one is a linear equation. Actually this is continuity of mass, means how the mass is changing inside the system, and remaining towards momentum balance equation. Okay, so these three equations together can represent change in properties or behavior of all kind of properties inside the system. Okay, and since it is bounded by two walls, so at the boundaries to solve this Navier-Stokes equation, we need some boundary condition. That can be different kind of boundary condition, maybe Dirichlet boundary condition, which gives us the variables are zeros at the wall, which is Dirichlet type boundary condition, or say the gradient of the velocity and velocity at the wall are somewhat proportional. In that case, we can find out the mixed type of boundary condition. Okay, or Robin type boundary condition. In some cases, you can say that gradient is zero. Okay, so such kind of boundary condition is called that normal boundary condition. So all possible boundary condition can be used depending on your flow type or application type. Okay. Now, once you have the set of equation, these three equation and boundary conditions, that set of equation is called Navier-Stokes equation, which model any kind of flow system that can be bounded, that can be unbounded, anything. If it is unbounded, then appropriately you have to choose your boundary condition. Okay. Now another thing is you can model a system. That is not an issue using the Navier-Stokes equation. But after modeling, how to find out the solution of this system? You have three different equations, some couple of boundary conditions. So how to solve this equation? And you know, solving Navier-Stokes equation is a very tough job. And till now, it is for a full Navier-Stokes equation, there is no analytical solution till now. It is an open problem. So, to solve the Navier-Stokes equation, the only possibility is you have to impose some methodology to modify the equation or to to find the limiting solution of the equation. That is the only possibility to solve the system of Navier-Stokes equation. Okay. So therefore, now I will tell you how to actually get a simpler equation from the Navier-Stokes equation and how to solve that simpler equation using linear algebra. Okay, and numerical analysis. Right. So we have three different equations and certain boundary conditions. Now our aim is to solve these equations using our known theory. And so since we cannot solve these equations directly, our aim is to modify these equations in mathematical way such that everything is preserved. That means you are not losing any properties or any mathematical process is not giving you trouble. Okay. So to do that, again, if you remember, first thing is we have to find out the initial solution or equilibrium solution of the system. And as I mentioned earlier, equilibrium solution is a certain kind of solution where the properties are not changing much more and they are time independent. At the initial stage, we can get this kind of solution. Therefore, you can find out the equilibrium solution from a simplified equation. And to simplify the equation, you have to use the assumption like equilibrium solution is independent of time. Equilibrium solution is not changing much with respect to other variables. And this solution is valid at the initial stage only. Once you are taking some different time, instead of 0 time, if you are taking different time, then this solution may not be valid. But in the initial time, if you consider all these assumptions, then you can simplify your equations. So we had these three equations. These three equations can be simplified to single equation if you consider your variables in such a way that for the equilibrium solution, say under equilibrium solution, your u is nothing but only function of y. It is changing only with respect to one variable and it is independent of other variable, and that can possible in equilibrium state because equilibrium state is very simple state, and in that case properties are not varying much with respect to the variables. Okay. So, and in that case your actually streamlines, if you remember the first figure, your streamlines will be again parallel. Okay. Therefore, the whatever variation is coming in one direction, so your u, which is the velocity in x direction, can be just function of y. And in this case, since streamlines are parallel or there is no disturbance, so in the perpendicular direction there is no velocity. So v is 0. Using these two things, if you substitute these two things, where capital U, V, Y is unknown and you have to solve, and that is your equilibrium solution. So you have to substitute these things in the governing equation, and governing equations are nothing but Navier-Stokes equation. So if you substitute in the first equation, say you are substituting the variables in the first equation, then we have noticed that your small u now in equilibrium state function of y only. So the first derivative will give you 0. Similarly, your normal velocity is 0 in the equilibrium state. That means the second derivative or second term also will give you 0. So the first equation is nothing but 0 equals to 0, which is a consistent thing. Okay. For the case of equilibrium solution, we are getting 0 equals to 0 from the first equation. That is fine. Now, if you the second equation, if you look the first term, you can see that we have mentioned all the variables in the equilibrium state are time independent as well as space. It is not much more varying with respect to space. So del u by del t will be 0 because u is only dependent on y. Similarly, del u by del x also 0. So first two term will not give you any contribution in the case of equilibrium solution. Third term also will not give any contribution because normal velocity or perpendicular velocity v also 0. So from the left hand side of second equation, you will get only 0. No contribution for the equilibrium solution. But there may be a contribution from this del p by del x and there may be contribution from other term. So del p by del x has contribution or may has contribution or may not have. So for time being, say this has no contribution. That means this P represent actually pressure inside the system. So total pressure with respect to X is not changing and therefore say this is 0. Now from all other terms, what we'll get? Only the non-zero term, that is del square u by del y square, because u is only dependent on y. Okay, so del square u by del y square equals to 0 will be the modified equation for the equilibrium solution. Similarly, if you check the derivative or contribution from each term of equation 3, you will get 0 equals to 0. Okay, therefore, finally, what we will get, because now our new variable u is ub of y. So we got only one equation from 3 equations, that is the second derivative of the equilibrium solution ub equals to 0. And from the boundary condition, Dirichlet boundary condition, you can get, or it is very obvious that ub equals to 0 at the boundaries. Okay. So getting equilibrium solution is very easy here. Once you take the limiting variables for the equilibrium solution, then you are getting a very simple homogeneous equation with two boundary conditions, and therefore the solution for equilibrium state capital UB is nothing but y square minus 1. Okay, since I have taken the boundaries at plus minus 1. Okay, similarly for the another variable PB, that means pressure at the equilibrium state, can be found as Cx. Okay, so similar process just apply and find out the solution for PB. But this is equilibrium solution, and once again I am telling this solution is initial kind of solution, and this is valid only in the equilibrium state or initial state. But in the Patav state, means more general state, if there is some disturbance to the system, then this solution is not valid. In that case, we have to find out the new solution. Okay, so say that Patav state or new solution is denoted by our variable small u. Then that small u can be written as the combination of two parts. One is equilibrium solution part and another is perturbation part, that is u cap. Similarly v cap and p cap. So these cap variables are denoting some correction to the solution or perturbation to the solution. So usually you can think about you are correcting the solution to get the appropriate solution of the disturbed system. Okay, so now we have to find out actually the quantities u cap, v cap, p cap, etc. Once we know that, then combination of the equilibrium solution and the perturbation will give you the general solution for the system. Okay, so to find out u cap, v cap, p cap, we have to first find out the equation for u cap, v cap and p cap, because they are the perturbation quantity and unknowns which is used to correct the solution. And these are just arbitrarily we are using these variables. So these variables must satisfy your first governing equations, that is the Navier-Stokes equation. So what I have done, I have with respect to perturbation in the governing equation, and from the set of you know that there is three different equations in the Navier-Stokes equation. From first equation I got similar kind of equation with respect to perturbation, that is hat quantities. All the hat with hat quantities are perturbed quantities for which we have to find out the solution. Once we know that solution, our job is done. So from first equation of the Navier-Stokes equation, we can find out equation 2. Similarly, from second part of the Navier-Stokes equation, we can find out equation 3, just substituting these variables and using the equilibrium solution, we can find out equation 3 and equation 4 as well. Okay, so these are coming after substituting our new variables, which are the combination of equilibrium solution plus the correction of part. And then using the solution, equilibrium solution, after simplifying, we can get equation 2, 3 and 4, which are coming from the Navier-Stokes equation. But you notice the yellow mark things. Why I have marked yellow? Because in these equations, equation 2, 3 and 4, in this equation, only these terms, yellow mark terms, are non-linear terms with respect to your unknown variables u cap, v cap and p cap. Only these terms are non-linear terms. Remaining terms are linear terms with respect to the perturbed variable u cap, v cap and p cap. So by this simple process, what we got, we remove the non-linearity of the Navier-Stokes equation at least by 75%, just substituting the variables, and we saw that there is very few terms which are still non-linear, and we have to somehow manage this non-linear term such that we can make much simpler this equation to solve it. Okay. So another thing, whenever you are thinking about perturbation or correction inside a system, you know that perturbations are small quantities. Okay. So since they are small quantities, if you are multiplying two small quantities, then they are becoming further small quantity. Okay. So since they are becoming further small quantities, so wherever the nonlinear term, that is product of two perturbation term or cubic term or square term, wherever they are present, we can omit that term or neglect that term because these terms are going to 0. So yellow mark terms are going to 0 because our perturbation quantity or perturbation variable u cap, v cap, p cap are very small, and therefore their multiplication is much smaller and going to 0. So we can omit this part to make this equation linear equation. And once you have linear partial differential equation, somewhat they are easier than non-linear partial differential equation, because for the case of non-linear partial differential equation, getting solution is much tough. Okay, so next part, what I have done, I have linearized the equation for the variables with cap to get linear equation, because the non-linear terms are very small here. And in this linearization process, I get much simpler equation which contains no non-linear term with respect to the perturbation quantities or with respect to the unknown variables u cap, v cap and p cap. So these are all linear equations. But still difficulty has not gone fully, because still you can see these equations are coupled equation. Why? Because the variables in each equation, the same variables are there, and you cannot solve these equations separately for one variable. So these are still coupled partial differential equations. So difficulty level has changed here from nonlinear to linear, but still there are certain amount of difficulties to solve this kind of equation, because these equations are coupled equation. So our next aim is to make decoupled, or to transform this equation to ordinary differential equation. Because in the case of wave equation, you remember that using trial solution, we have transformed the partial differential equation to ordinary differential equation first, and then we look for the eigenvalues and eigenvector of the stream-Liouville problem. Okay, so here also our aim is same. We'll use some trial solution or normal mode solution to transform this partial differential equation 5, 6, 7 to a particular ordinary differential equation of stream-Liouville type, such that we can solve for eigenvalue and eigenvectors. Okay, so as I mentioned earlier, for the general case, the normal modes behavior, there is a part. So just quickly let me show that part once again. So if you see this, so in this case, the trial solution has one amplitude part u of y and exponential part which is x dependent on x and t. Okay, so we can use this generalized trial solution to simplify our set of coupled partial differential equation. So if we use that normal mode solution here and do the algebra, differentiate with respect to x, the equation 6, differentiate with respect to y, differentiate with respect to y to the equation 6, and differentiate equation 7 with respect to x, then add those two equations and then use the trial solution, then what will happen? This one variable we can decrease, this pressure term will go if we take the gradient in these terms and add. Then this one variable p cap can be removed using simple mathematics. Okay, after removing this p from these equations, differentiate equation 6 with respect to y, differentiate equation 7 with respect to x, and then add. That will give you or subtract, that will help you to remove the variable p. So in this process, what we can do, we can decrease the number of variables also, because once we can solve for one variable, since these equations are coupled, we can solve for other variables. But if we do not remove one variable, then we have to solve all the equations together, which is very difficult. So in this process, we can remove p from these three equations, and after that, if we use that particular type of trial solution, after algebra, we can end up with a final equation, final ordinary differential equation, so which is a stream-Liouville type equation marked in red color, equation 8. So which is a stream-Liouville problem, and this is a single variable problem, because see, we can remove all two variables u and p with this particular way, and we end up with a equation in one variable v, and this is a ordinary differential equation. All the differentiation or primes are with respect to y. Okay, so this process is little bit lengthy, so I am not going to discuss all those things, but this can be possible from three different partial differential equations using the trial solution and certain algebra. We can end up with a ordinary differential equation of order 4, order 4, and that is a equation of stream-Liouville problem type problem, where C, this C is the eigenvalue here, and all others are alpha is a supplied parameter and V is the unknown. So this is a Liouville problem with V as unknown and C as the eigenvalue. Okay, so now our aim is to solve this equation by help of eigenvalue, eigenvector. Okay, so to do that, there are certain approaches, analytical approaches as well as numerical approaches. But if your problem is very simple, then you can use analytical approach to get the solution from that eigenvalue problem. But if your problem is somewhat complicated, then it is not possible. Okay, analytically. So in analytical approach, you can apply some other method also, like Taylor expansion or some weighted method, residual method. But these are very complex method, and for the case of complicated problem, you cannot apply directly this analytical method. So other possibility is you have to apply some numerical methods, and there are certain known methods to you, like RK method, Euler modified method, etc., to which can help you to solve the fourth order ordinary differential equation, which is the final equation for our system. But in this process, in this numerical process, there are certain difficulties also, because these processes are very lengthy for this kind of flow, this kind of problem, and sometimes you cannot get accuracy also. Therefore, you have to choose a particular method which is very useful this kind of problems, or this kind of fourth order ordinary differential equation which are eigenvalue problem. That is Chebyshev spectral collocation method. So using this method, you can find out numerically eigenvalues as well as eigenvector of the system, which is the final equation. This is the final equation, and you can find out eigenvalue C and eigenvector V, because V is the unknown, so that is the eigenvector, and C is the eigenvalue of this system. So you can find out numerically C and V using this Chebyshev spectral collocation method. This is a simple numerical method which will help you to find out the eigenvalue and eigenvector numerically. Okay, but if once again I should mention here, if your problem or equation is very simple, as we have seen earlier examples, then analytically you can find out your eigenvalues and eigenvector. But if the problem is complicated, in this equation is much complicated equation. So in this case, analytical solution is very difficult. So analytically you cannot find out eigenvalue and eigenvector. Therefore, you have to take help of some numerical methods, and most useful method is for this kind of problem is Chebyshev spectral collocation method. And since it is a spectral collocation method, so easily you can find out the spectral or eigenvalues using this method. And once you know the eigenvalues, you can find out the eigenvectors corresponding to the particular eigenvalue. Okay, so just quickly, little bit I should tell about this method. So I should not tell much more about this numerical method, but you can think of, there is the method which can help you to find out eigenvalues and eigenvector of a very complex differential equation of stream-Liouville type, to find out the eigenvalues and eigenvector. So in this method, actually what we'll do, we'll discretize the equation in a domain, say -1 to 1, using Chebyshev point. And Chebyshev points are nothing but particular type of point given by this Yj, which points are equally spaced between -1 to 1. Okay, and why we are using this Chebyshev polynomial? Because Chebyshev polynomials has a very important property, that is orthogonality property, and which will help us to convert this differential equation to a system of differential equation. System of equation, linear equation. So actually we have this complicated equation, equation 8. Now we want to solve this equation. Analytically it is not possible because this is very complex equation. So we are trying help of numerical method, that is called Chebyshev spectral collocation method. With this method we can discretize the equation, and we can, once you discretize, you know that from numerical analysis, if you discretize a domain, and if you are interested to solve a differential equation, then you can end up with a system of equation. Okay, so my aim is also here same. I want to get system of linear equation, because I know once I have a system of linear equation, then how to solve system of linear equation and how to get eigenvalues and eigenvector, that is unknown to us. So in this discretization process, we'll end up with a set of equation, linear equation, and that set of equation has two different matrices. This is a generalized system of equation. Ax equals to c into bx, where a, b are coefficient matrix and c is the eigenvalue and x is the set of unknowns. You are familiar with system of equation like ax equals to 0 or ax equals to b, where a is a coefficient matrix, x is set of unknowns. In first cases, ax equals to g is homogeneous system of equation. In second case, if you consider ax equals to b, that is non-homogeneous equation. And you already familiar from the earlier classes that how to solve system of linear equation using eigenvalues, eigenvector. Okay, so here this system of equation also similar like, but it is called generalized because you can see the matrix has two parts, A and B, and this is an eigenvalue problem because I am writing the form in such a way that Ax equals to C into Bx. So this generalized eigenvalue problem has eigenvalue C and eigenvector X. Okay, maybe many of you is familiar with general eigenvalue problem. So this is called generalized system of linear equation, and this is nothing but a generalized eigenvalue problem where A, B are coefficient matrix, C is the eigenvalue which we have to find out, and once we know the C, then we can find out eigenvector X. This eigenvector and eigenvalues will give us the appropriate solution or general solution of the differential equation. This is the overall idea of the Chebyshev spectral method. Now we have the system Ax equals to C into Bx, and we can solve this numerically. Say we able to get the values of C, and then for each values we can find out X, then our job is done. So I want to omit few slides here. There are more details about the Chebyshev expansion. So I don't want to mention all those things. But if you are interested, then you can look for some numerical analysis book to get this numerical method, how to actually apply this numerical method to convert the differential equation, complicated differential equation, to the system of equation, generalized system of eigenvalue problem. Okay, that you can do if you see this method. So I want to omit these slides here. So at last I want to give the behavior of the eigenvalues and eigenfunctions. As I mentioned earlier, we have a eigenvalue problem, generalized eigenvalue problem. Ax equals to C into Bx, where A, B are coefficient matrix, C is the eigenvalue, and capital X is the eigenvector. So after solving, you can use MATLAB or any other software to solve that system and to find out the eigenvalues of that system, because analytically it is not possible. When you are discretizing the system, you have enough number of points or huge number of points. So matrix A and B are a big matrix, square matrix, but they are very big matrix, maybe say 50 cross 50 or 30 cross 30 or 40 cross 40 matrix. So analytically it is not possible. You can take help of any software like MATLAB or Mathematica to find out eigenvalues of the matrix A, B for the generalized eigenvalue problem. And in the first figure, I have plotted the eigenvalues corresponding to the problem. That means all the C. Since the matrix is a 30 cross 30 matrix after discretization, then you will get 30 eigenvalues, because order of the matrix is 30 cross 30. So you can get 30 eigenvalues. So that eigenvalues, if you plot, you can check the behavior of the eigenvalues. And one thing you must notice that if the eigenvalues, so here only one eigenvalue, such eigenvalues is present. If the eigenvalues are positive, so see one eigenvalue is greater than the above the zero line, all others are below the zero lines. If you can get some positive eigenvalues, then for that positive eigenvalues, you can find out unstable solution of the system. But if you are getting all the eigenvalues are negative, then never you can get unstable solution. All the solution are stable solution. So depending on the behavior of the eigenvalue, if you plot the eigenvalues, you can guess the behavior of the solution. And once you choose a particular eigenvalue, then you can plot the particular eigenfunction, so which is done in below figures. So these are the eigenfunction behavior or solution behavior, and different curves I have plotted because I have plotted imaginary part, real part of the eigenfunction and absolute part of the eigenfunction. So you keep in mind that in this case, usually you have studied that real eigenvalues and real eigenvectors, but in this generalized system, actually you can get complex eigenvalues and complex eigenvectors. So that's why I have plotted CR versus CI, because our C is the eigenvalue and C equals to CR plus ICI. So I can plot CR versus CI. So these are the eigenvalues, complex eigenvalues. Corresponding to a particular eigenvalue, this positive eigenvalue, I have plotted the eigenfunction, real part, imaginary part, and absolute value of the eigenfunction. So these are the typical behavior of the eigenfunction plotted here. And using these eigenvalues and eigenfunction, so many more details also you can study for this kind of problem. Once you have set of eigenvalues, you have idea of set of eigenvalues as well as set of eigenvectors, then further physical insight you can do. So few figures I want to show here. Say you know the most positive eigenvalue. Okay. Now, if you can plot with respect to the parameter, you remember that there was a parameter called alpha. With respect to parameter alpha, if you plot the eigenvalues with positive magnitude, okay, you or say positive eigenvalue, if you can plot with respect to alpha, then you can see certain behavior of the eigenvalues. And depending on this behavior, you can conclude some instability behavior that I am not going to discuss here. So these are more advanced things. So using eigenvalues, actually you can find out some growth rate or some boundaries. Inside the boundaries or region, you can guess the stability or instability of the system. Okay. Similarly, using eigenvectors also, you can get some physical insight. Using eigenvectors inside a system, you can construct energy of the system. Okay. So once you know the eigenvectors or eigenfunction of this system, then you can find out the solution, and that solution can be used to find out the total energy or disturbed energy inside the system, and you can calculate the energy also. Okay. And based on the energy, you can tell about what is the source of instability inside the solution, that you can control also. So all those things are much advanced things. So you can, if you want, you can read these things, how the eigenvalues and eigenvector of a complex differential equation can be useful to study various physical phenomena inside the system. And those are very interesting actually. So later on you can look into these things, this stability theory and use of eigenvalues, eigenvector, and linear algebra, means system of equation, how system of equation are useful in various problems. So that things you can look into, and if you have any interest or if you want to actually ask any justification or any discussion about this kind of things, you can write mail to me. So I think I want to stop here. I don't want to discuss much more things. So I want to stop here. Maybe I have finished just 15 minutes before, but I'll be happy if people are interested in some discussion regarding this theory.
Thank you, Dr. Sukhendu, for these wonderful talks. Now floor is open for question answers. Any questions, participants?
So participants, you can ask question, whatever doubt you have in your mind, because this is a new area, and you can see that lot of application of mathematics like linear algebra and differential equation. So if you have any kind of doubt, you can ask me.
So I'm going to stop streaming now so that now stream has been stopped. So now I'm not recording anything. So you are free to ask questions to